Hi class, it's me, Mr. Morris. Bear with me, I'm kind of learning some new technology here today, but we are going to go through just a little bit of a review of what we did last class, the elemental composition of pure substances. We did the first page. I'm not going to go back through it, but just to remind you what it was. We talked about this formula for the percent mass of element in a compound. And a few different ways we can do it. We could give you some lab data where I give you grams of, let's say, grams of calcium, grams of sulfur, grams of oxygen, and then we have the grams of a particular compound. Okay. We could also have, and then you would just do the mass of calcium divided by the mass of the compound times 100. Do the same thing for sulfur and oxygen. We can also find it from its formula in the case like we have here on the second example problem. You have the formula, so we just use the periodic table to take the mass of copper divided by the molar mass of copper nitrate, if you add that all up, and then multiply by 100. Same thing for nitrogen, because we have two nitrogen atoms in that compound, we would need to double the mass of nitrogen. And then, of course, oxygen, this last one right here, would be 6 times the mass of oxygen, because, of course, we have 3 oxygen atoms in each nitrate, and there's 2 of those. So it's a total of 6 oxygen atoms. Again, we did that last class, so we don't really need to bog down in it. Not sure what's happening here. Let me get away from that. All right. Now let's look at an example problem. Well, we already did this one. We wanted to find whether lithium chloride or potassium chloride would have a greater percent mass of chlorine. And we talked about this last time, but just to put it in words, lithium chloride has a greater percent mass of chlorine because the molar mass of lithium chloride is lower than the mass of potassium chloride. Our formula is percent mass of chlorine is the mass of chlorine over the mass of the compound times 100. And since both compounds contain the same mass of chlorine, the only thing that could be different is the mass of the compound. So the mass of the compound with the lower molar mass will give you the greater mass percent of chlorine. We did the same thing with H2O and H2O2. Use very similar logic. We're wanting to know the percent mass of hydrogen. Now we've got 2 hydrogen atoms, but it's the same amount of hydrogen in both compounds. So the only thing that changes is the amount of oxygen. So the compound that has a smaller overall mass of compound, a smaller molar mass, is going to give you a higher percentage of, and that should say percent mass of chlorine, not percent mass of hydrogen. Sorry about that. Or it says percent mass of chlorine. It should say percent mass of hydrogen. But the explanation still stands. All right, on the second page, we're talking about something that we have talked about before in a sense, but not in these exact terms maybe. The law of definite proportions. It tells us that the ratio of the masses of constituent elements in any pure sample of that compound is always the same. So if we have a true pure substance, that means it's a compound. The ratio of the masses has to be the same. If it's a pure sample, it has to always be the same. For any samples of a pure compound, the percent mass of elements that make up the compound will always be the same. So we've got examples. One down here is for sodium chloride. We have the mass percent of 39.34%. And then a student analyzes, this is our accepted percent mass of sodium, right? Accepted percent mass of 39.34%. Student analyzes a 2.50 gram sample, and he found that it contains 1.23 grams of sodium. Could this be NaCl? The only way we would know is by comparing their percent masses. So We find the percent mass of sodium by taking the mass of sodium divided by the mass of the sample and multiplying by 100. So we did 1.23 over 2.50 times 100, and we get 49.2%. Now that's not the same percent as the percent that was given in the problem. It's not 39.34%. It's 49.2%. So this could not be NaCl because the percent yield is not the same. So that goes back to the concept we're talking about here, that if you have a pure sample of a compound, the percent masses have to be the same. Now we got another problem down here. We're flipping it around the other way. It says the elemental mass percent for glucose is 6.7% hydrogen, 40.0% carbon, and 53.3% oxygen. A pure sample is analyzed, and it has the same percent masses of hydrogen, carbon, and oxygen. The student concludes that the sample is glucose. Do you agree or disagree with the student's conclusion? Explain. So pause the video and think through that for a little bit before I go and answer the question for you. Well, we can see it does have the same percent, right? So we have the same percentages. That's an indication that it could be the same sample, because we know that if it's the same compound, I said sample, if it's the same compound, it has to have the same percent. But does having the same percent mass necessarily mean it's the same compound? Well, based on just what we talked about, you maybe wouldn't know, but we've talked about something called empirical and molecular formula in the past. We have a hydrogen, a carbon, and an oxygen. Those are all nonmetals, and we don't have a polyatomic ion involved in this. So this is a covalent compound. That's important. We cannot conclude that the sample is glucose, although it may be glucose. All we can conclude is that the compound shares the same empirical formula as glucose because it is a covalent compound. It could be the same, but it could have a different molecular formula. I want to review those details with you now. I'm sure that this may be a little confusing at first for some of you, especially if empirical and molecular formulas are a little bit rusty in your mind, a little bit far back in your mind. So we're going to go through and review what an empirical formula is and what a molecular formula is, and why this question is not quite as cut and dried as it looks. It could be the same pure substance, but it also could be a different pure substance with the same empirical formula as glucose. We're going to talk about that down here when we explain and just review what the empirical and molecular formulas actually mean. All right, so continuing on with empirical and molecular formula. The empirical formula is the formula with the simplest ratio of elements, and the molecular formula, that's the actual formula, the formula with the actual number of atoms of a given element in the molecule. Most ionic compounds are the empirical formula because in ionic compounds, the ions already have to be balanced in the smallest number ratio. So just remember that ionic compounds, that's why we simplify them. It's because their charge has to be canceled out, so we simplify it to the smallest whole number ratio. This is the method for finding the empirical formula given the percent composition. And I want you guys to catch, you can start at any point in this process. Let's say that I'm given moles. I would start at step 3. If I was given grams, I'd start at step 2. You start at whatever point in this process that that pertains to the information that you've been given in the problem. We'll do some examples. But there's a lot of steps here. I think that the easiest way to remember it is this poem here on the right-hand side. Percent to mass, mass to mole, divide by small, and multiply till whole. It's just an easy way to remember the steps, and we'll go through and remind ourselves what they mean. Once you find the empirical formula, you can find the molecular formula as long as you know the molar mass. Because the empirical formula has to be multiplied by some whole number to come up with the molecular formula. Again, we'll do some examples. Hopefully that'll ring a bell. So our first examples, a compound is found to have a mass of 48.38% carbon and 8.12% hydrogen, and the rest is oxygen. Now, if we say the rest, that means the remaining percent. So we could do 100 minus those numbers, and we would be able to get the answer. So we've got that worked out right here on the screen. 100 minus 48.38 and 8.12, you end up with 43.50% of it that is going to be oxygen. Right? Now, we've done the first step for you. That was going from percent to mass. You just write it in terms of grams. We're assuming that there's 100 grams of the substance. The next step is to convert those grams into moles, and we've done that in step 2. And then we've got all 3 of these numbers of moles. The third step says divide by small. So we're going to pick which of these is the smallest number, and it looks like the smallest number is this one right here. So we're going to divide by 2.719 moles for each of them. 2.719 moles, 2.719 moles. When we do that, we'll get our answers. The last one is going to be 1.00. Okay, 8.06 over 2.719. That gives us 2.96, which is about 3. And if we do 4.028 divided by 2.719, we end up with 1.48. Okay, a lot of times this is kind of the end of the process, because a lot of times that just simplifies it down to a nice whole number. But step 4 is done when needed, and that is when you don't have a nice whole number. Well, 1.00 is an exact whole number. 2.96 is close enough, we could call it 3, but 1.48 really isn't. So what we want to do is multiply by something that will bring it really close to a whole number. So I see that 1.48, that kind of looks like pretty close to 1.50. If I were to double that, I could get a whole number. So I'm going to double this. But if I double that, I've got to double all of them. And by the way, this is what step 4 is multiplying by whatever number it takes to make these whole numbers. So 1 times 2 gives us 2. 2 times 2.96 is about 3. Multiply that by 2. 3 times 2, it's about 6. And then 1.5 times 2 is going to be about 3. So if we zoom back out and see what we're looking at, we have about 3 moles of carbon for every 6 moles of hydrogen and 2 moles of oxygen. So our empirical formula is C3H6, and then O2. That's the simplest whole number ratio of those 3 elements to each other. Now it gives us the molar mass of the molecule. Molar mass, keep in mind, the molar mass of the molecule, that's of the actual molecule. What we have here is the empirical formula we came up with. But the molar mass of the actual molecule is this. We want to know what the molecular formula is. So if you'll go back up to our formula, empirical times N equals the molecular formula. So that's what we're going to use. Empirical times N equals the molecular formula. We have that down here. It's written again. The molar mass of the molecular formula is 222.27. The molar mass of the empirical formula we would have to look up. That would be carbon has a mass of 12.01. And we want to multiply that by 3 because the empirical formula has a subscript of 3. Plus hydrogen has a mass of 1.008, and I'm multiplying that by 6 because of the subscript of 6. And then oxygen, O2. So oxygen is 16 times 2 because of the subscript of 2 in our formula. We get 74.078 grams per mole. So if we know the molar mass of the empirical formula, 74.078, I could multiply that by N, that's our unknown, and it should multiply together to give us 222.27. So if I want to solve for N, I just have to divide. So N equals, and that's going to be both of those sides, we're going to just divide by 74.078. It cancels that out, 74.078. So we have 222.27 divided by 74.078. We get 3. So if that number is 3, then over here when I write the formula, I'm just going to write my empirical formula, which is C3H6O2, and I'm going to multiply that by 3. 3 times 3 is 9, so I have C9. 6 times 3 is 18, so we have H18. 3 times 2 is 6, so we have O6. And that's our molecular formula, C9H18O6. All right, that's the gist of what you do with empirical formula. Something really similar is a hydrate. A hydrate is a little different. It's a substance that includes water in the formula. Water is not actually part of the chemical substance, but it's important to be able to identify how many molecules of water we have for each molecule of that substance. So this formula means that for every Na2S in the piece of the substance you're holding, there's also 9 water molecules. It's not wet. It actually seems to be dry. Some of them are different colors, but it just looks almost like a normal salt. Okay, there are some hydrates that have a wet appearance. Most of the time, they look to be dry and they feel dry because the water molecules just absorbed. Okay, the water molecules can be removed from the hydrate crystals by heating, and you'll be left with the salt. So there's supposed to be an arrow there. It was replaced by that question mark, but the yield sign, Na2S, and then it's got 9 waters, so we would call that nonahydrate. It would break up into Na2S plus 9H2O. And if we were to heat it enough that it would do that, we'd probably get solid sodium sulfide, and we would get gaseous water, water vapor. So the dry salt would be left behind, it would be called an anhydrous salt. That means that it doesn't have any water left in it. We removed the water from the hydrate. Now it tells us how to find the hydrate formula. We did learn this last year, but it was very, very quick, I believe. We can use the technique that we learned in determining the empirical formula to find the ratio of the ionic compound and the water molecules. Only use the first 3 lines of the poem. The ratio is always going to be 1 to X. So our example, we have lead 2 perchlorate, and it's some hydrate. We don't know how many waters we have, but we know the percent of lead perchlorate, and we know the percent of water. So we're going to do what we did in empirical formula, percent to mass, mass to mole, divide by small, and we skip that last step. So percent to mass, we turned it into grams down here. Mass to mole, divide by your molar mass to find the number of moles. And then we're going to divide by the smallest number. So it looks like our smallest number is PbClO4 By the way, it is always going to be the ionic compound that's the smaller of the 2 numbers of moles. Okay. In step number 3, we're going to divide both of these numbers by the smallest one, which would be 0.2173. Of course, this is going to be 1. If we divide that, looks like it's going to be about 3. So it's not exact, but it's about 3. So our formula is going to be PbClO4 and then we have that X we're replacing with the number 3. We do a raised dot. That doesn't mean multiplied by. It's just the way that we write hydrates. It just means for every PbClO4 we have 3 water molecules. Okay, note that steps 1 and 2 of the poem in solving the empirical formulas or hydrate formulas, if the problem provides the masses, so keep this in mind, if it provides the masses instead of percent to mass, just start with mass to mole. If it provides the moles instead of the percent, mass, or the mass, we're just going to start with divide by the smallest. You start wherever you're at. So here's an example of that. In an elemental analysis of a sample of a pure compound, we have 0.336 moles of Al, 1.008 moles of Cr, and 3.528 moles of O. So in our poem, we say percent to mass. Well, I don't have any percent, so I don't need to worry about that. And then it says mass to mole. Okay, mass. Nope, this is not units of mass. To moles. Oh, I already have moles. I'm just going to start right there. So I'll write down 0.336 moles of Al. And then I have 1.008 moles of Cr. And then I have 3.528 moles of oxygen. Okay. So what do we do at this point? Just divide by the smallest one. So we're going to be dividing by 0.336 moles. 0.336 moles, because we skipped percent to mass and mass to mole, we just divide by small. And we'll see what we get. Well, this is going to equal 1 because it's that divided by itself. Okay, 1.08 over 0.336. You probably could guess it. That's going to come out to be 3. It's actually exactly 3. And then the other one, 3.528, that's going to be pretty close to 10. 10.5 actually. So I would have guessed that wrong. So this comes out to be 10.5. Well, what's the problem with this? We don't have whole numbers, so we're going to have to multiply till whole. What would we multiply this by? Well, I have a half integer here. I'm going to multiply it by 2, multiply this by 2, multiply that by 2. So I end up with 2, 6, and that would be 21. So I have Al2 Cr6 O21. Go down a little bit farther. 802.5 grams of hydrated zinc sulfate was heated. Let's back up. Here's another example. We could probably go through this one together in class, so I'm going to skip over that, and we'll see if we can go through that in class. Combustion analysis. Now this is something really similar. We did a problem that was like the first step in combustion analysis, but we're going to put it all together in this example. Combustion analysis is when you have a hydrocarbon, which is made of either carbon and hydrogen, carbon, hydrogen, and oxygen, or carbon, hydrogen, oxygen, nitrogen, or any combination of those elements. So it's hydrogen and carbon primarily, but sometimes there's some oxygen and nitrogen in it. Combustion analysis is when you burn it in the presence of oxygen, and we analyze the amount of product that we get, and we try to figure out what the formula is. So it requires that you burn an unknown substance and trap the gases from the burning. We'll calculate the empirical formula for the substance. There are some points to make about combustion analysis. The elements making up the unknown substance almost always includes carbon and hydrogen. This is almost always the case. Oxygen is often involved, nitrogen is sometimes. There's other elements sometimes, but those are the most common ones. We have to know the mass of the unknown before we can burn it. It doesn't do any good if you don't measure the unknown before you burn it. The unknown will be burnt in pure oxygen present in large excess. So we want oxygen to be our excess reactant so we can properly analyze the unknown sample. Carbon dioxide and water vapor are the products. Nitrogen gas is the usual product if there's nitrogen involved. And the combustion products usually are CO2, H2O, and N2. Any of those might be involved. They're trapped separately from each other, and the mass of each combustion product will be determined. All of the carbon from the compound winds up as CO2. We talked about this the other day. All of the H turns into H2O. All of the N turns into N2 if we are doing combustion analysis with a nitrogen compound. So the calculated mass of carbon from carbon dioxide will be the amount of carbon in the hydrocarbon. Same thing for hydrogen in water and nitrogen in the gas nitrogen, N2. Oxygen is part of the unknown compound. If oxygen is part of the unknown compound, then all of the oxygen from the compound, along with some of the oxygen gas used for the combustion, ends up being in CO2 and H2O. So that's a little trickier to figure out. The only way to do it is by finding the other substances first, and then we would subtract. So the mass of O would be determined by subtracting the mass of the compound with the masses C, H, and N. Using masses of all of the elements that made up the compound, the empirical formula can be determined. So let's do an example of that. It's very similar to something we did the other day, but let's go back through this. Okay, so I have 4.40 grams of CO2. Remember, that's where all of the carbon comes from, or where all of the carbon goes. I have 2.70 grams of H2O. and it asks what is the empirical formula of this compound. First thing we have to do is find how many moles of CO2 that we have. So we've got to use the molar mass of CO2. I believe it's 44 point something. See, it's 12.01 plus 16 times 2, which would be 32. So yes, it's 44.01 grams of CO2 for every 1 mole of CO2. And for every 1 mole of CO2, we end up with 1 mole of carbon, because there's 1 carbon atom in a CO2 molecule. All right, here we have grams of H2O. We want to put the mass of H2O on the bottom. So H2O is 1.008 times 2 plus oxygen is 16. We get 18.016 grams of H2O for every 1 mole of H2O. And for every 1 mole of H2O, we ended up with 2 moles of H atoms. So 4.40 times 1 divided by 44.01 times 1 over 1, that ends up being 0.0999 and so on. Okay, so to 3 significant figures, it actually ends up being 0.100 if we round to the correct number of sig figs. And then I have 2.70 times 1 over 18.016 times 2 over 1, and I end up with 0.2997, which to 3 sig figs is 0.300. All right, and this is moles of carbon. This is moles of hydrogen. All right, remember the rhyme for the empirical formula: percent to mass, mass to mole, divide by small, multiply till whole. Well, at this point, I have my moles. So the only thing that's really left to do is divide by the smallest, which would be 0.1. So I end up with 3, and right here I end up with 1. So our empirical formula is CH3. All right, we have another example of a combustion analysis, example 2, and then we have an observed molar mass, so we could find the molecular formula. These are very similar to the types of problems we've done before, but we're doing combustion analysis. I'll try to cover those in the next class. I might make a video so that you guys have the option to watch it before then, but that's it for the notes for today. Let me know if you have any questions about them.